welcome back to this Forge College Explainer. So, in our previous lesson, we accomplished something huge. We successfully built our core program logic in Rust and Anchor. But, as any seasoned developer knows, having logic that simply compiles, that's literally only half the battle. The other half is actually proving it won't just instantly break the moment someone looks at it funny. So today, we're going to draft the blueprint for an automated assembly line, one that ensures your Solana program works exactly as intended every single time. Let's get into it.
Here is our agenda for today. We'll be covering 1. From logic to launch. 2. Automated behavior-first testing. 3. Scripting reproducible deployments. 4. Continuous integration pipelines. 5. End-to-end validation. And 6. Wrapping up. All right, Section 1. From logic to launch. Drafting the pipeline blueprint. Okay, so there is a really stark contrast we need to talk about here. If you're coming over from the Ethereum world, you might be super used to ad hoc testing, right? You know the drill. Deploying to a testnet, poking it with a stick in Remix, and just kind of hoping it doesn't explode. Well, that manual, click and hope tinkering, it's notoriously fragile. What we really need for our blueprint is behavior-first testing. This is a highly automated approach that rigorously mirrors EVM semantics. It makes absolutely sure your Solana program automatically throws the exact right error code under the exact right conditions. No guesswork allowed. Now, our ultimate philosophical goal for this entire pipeline is creating what we call a reproducible artifact. Think of this as the holy grail of Web3 verification. It's the exact set of files, meaning your compiled binary, your program keypair, and your IDL, that lets literally anyone recreate your exact program ID and run the exact same transactions without having to mess around with their local environment. Because in the eyes of Web3, if it's not reproducible, it didn't really happen. Let's move to Section 2, Automated Behavior-First Testing. The testing floor. It all starts with a clean environment. By running solana-test-validator with the -reset flag, we are guaranteeing a pristine local ledger. That means no lingering phantom accounts and absolutely no mystery state left over from yesterday's 3 a.m. coding session. Just a perfect blank slate for your tests to run on. With that blank slate ready, the testing flow really operates like a well-oiled machine. First, you fire up that validator. Second, you run the anchor test harness, which handles the heavy lifting of locally deploying your program. Third, you execute your integration tests. And fourth, and this is super important, guys, you have to strictly assert both your successes and your negative error paths. A test suite that only checks if things go right is, frankly, lying to you. We have to mathematically prove the program securely rejects invalid actions, too. On to Section 3, Scripting Reproducible Deployments, the packaging machine. We achieve this reproducibility by writing a deterministic deployment bash script. It acts kind of like a mechanical sequencer. Step 1, it builds the program. Step 2, it mechanically checks that the compiled binary actually exists. Step 3, it uses a specific committed keypair to deploy the program. This is what locks in your program ID, so it doesn't just randomly change every single time. And finally, Step 4, it zips all these results up into a neat release file. So what exactly goes into that package? Well, these are the essential artifacts your script absolutely must produce. You've got your .so file, that's the compiled executable binary, then the program keypair.json, which is what guarantees that reproducible program ID. You also need the IDL file, mapping out accounts and instructions for any client applications. And finally, the release zip itself. Anyone who downloads that zip file essentially holds the entire DNA of your program. Next up, Section 4, Continuous Integration Pipelines, the automation robot. Now, running scripts manually on your laptop still leaves way too much room for human error. Forgetting to save a file or dealing with slightly different local Rust versions. So we're going to introduce an automation robot. By configuring a simple GitHub Actions workflow, on every single code push, this robot will automatically install the exact right toolchains, run our tests, and build our release zip. It ensures your program actually works on any machine, not just yours. Now for a quick warning. When you set this up, your CI pipeline will inevitably turn red and fail the first time. It happens to all of us. Resist the urge to throw your computer out the window. It's just the robot doing its job. When it happens, check these classic engineering headaches. Did you allocate the wrong space for an account? Did you maybe forget to update the program ID in your IDL? Did you leave your local pair with insufficient lamp ports? Or are your CLI versions mismatched? Running through this checklist solves almost all initial CI failures. Bringing us to Section 5. End-to-end validation. Quality control.
All right, this brings us to the ultimate multi-million-dollar Web3 question. It's super easy to get caught up in green checkmarks and zip files, but we have to step back and ask, did the deployed program actually do what it's supposed to do? Like, does our newly ported EVM logic functionally operate in the live, chaotic Solana environment?
To answer that with absolute confidence, we look for 3 non-negotiable success criteria. First, automated tests must pass locally with an exit code of 0. Second, the deployed public key has to perfectly match the committed key pair, because if it's different, your deployment just isn't deterministic. And third, you must run a real sample end-to-end transaction from a client script against that live deployed program to successfully execute the expected state transitions. When all 3 of those hit, your quality control is absolutely pristine.
Finally, Section 6, wrapping up your capstone, the sign-off.
I want to leave you with this golden rule right here. Reproducibility means the exact set of files should allow someone to reproduce the same program ID without any manual environment fiddling. Your code, your tests, and your deployment artifacts, they must speak entirely for themselves. Anyone reviewing your work should be able to type one single command and watch your flawless engineering unfold exactly as intended.
In our next step, we're going to synthesize these artifacts into your final deliverable documentation and comparative analysis. This explainer was made by Forge College, and I highly encourage you to visit forge.college to learn more about this capstone process and tons of other amazing Web3 topics. But to wrap up today's session, I'll leave you with this thought. If a smart contract is deployed in the forest and there's no reproducible artifact to prove it, did it ever really happen?